DCT basis functions. 64 fixed basis functions are used. Each block of the image of the size 8 cross 8 is expressed as a linear combination of basis functions. While compressing 64 weights of linear combinations are calculated. Weights are threshold. Um, the threshold value provides the degree of conversion, that is select decide irrelevance. Example: cameraman, image black, image black, image intensities, image intensities. Here 185, 187, that is from 1 to 8, 1 to 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Here 185, 187, 184. Actually here starting 10, 10, 11, 17, 26, 29, 29, 50. So like this. So low is high pixels. Here low. Here. Example: cameraman, DCT, image intensities. So here this portion intensity is different, this portion is intensity is different from this. Intensity, image intensities 1 to 8, 1 to 8. Here coefficients of the DCT2, coefficients of the DCT2. Here also say 1 to 8. Here -1, 7, 2, -9, 22, 28, -46, 30. Coefficients of the DCT-D2. Example: cameraman 10% in a 50%. 100% of most significant DCT2 coefficients. 50% of most significant DCT2 coefficients. 50% most significant DCT2 coefficients. Here 100% of most significant DC2 coefficients. Here 20%, here 5%, 20% of most significant DC2 coefficients, 5% of most significant DC2 coefficients. From 5% to 20% is better. From 20% to 50% is better. From 50%, 100% is better. That is 100% of most significant DC2 coefficients. JPEG example. Here JPEG example K equal to 3.8. After reconstruction K equal to 3.8, predictor error. K equal to 3.8, predictor error. JPEG example K equal to 4.2. Here 3.8. So improved is the predictor error. After reconstruction K equal to 4.2. After reconstruction K equal to 3.8. JPEG example K equal to 5.6. After reconstruction K equal to 5.6. Predictor error here. Okay, this is K equal to 5.6. This is the predictor error. K equal to 10.2. Here after reconstruction K equal to 10.0, 10.2. Predictor error. This is the predictor error. So in predictor error 10.2, K equal to 10.2, K equal to 5.6, K equal to 4.2, up K equal to 3.8, like this. Image compression. I will say another one examples. image compression. Images and videos in raw, uncompressed format have very large data. Images and videos in raw, uncompressed format has very large data. Image video size. Here, one page of text, 16 KB. Standard 640 cross 480 24-bit color image 7.3 MP. FHD 1920 into 1080 24-bit color image 49.3 MP. Animation 50 Mbps 50 megabits per second. Standard video 227.6 megabits per second. Transmission and storage of such large data is not easy. Transmission and storage of such large data is not easy, so compression techniques are used. Principle of communication. Actually, principle of compression. Compression is achieved by exploiting one or more of the following: coding redundancy, spatial and temporal redundancy, information irrelevant to human visual system. Types of compression: lossless compression, reversible, information preserving, text and binary images. Lossy compression, irreversible, most image and video compression methods. Nearly lossless compression for medical images. Goals of compression: given a data amount, achieve the best quality. Given allowed distortion, minimize the data amount. Once again, given data amount, achieve the best quality. Goals of compression: given a data amount, achieve the best quality. Given allowed distortion, minimize the data amount. Some distortion methods: mean absolute error, MA equal to 1 by N, summation of I equal to 0 to N minus 1, X of I minus Y of I. This is the mean absolute error. Okay. And then mean squared error. MS equal to mean M for mean, A for absolute, E for error, M for mean, S for squared, E for error. 1 by N, that is total N taking one value, its meaning. Then multiply with from summation of I equal to 0 to N minus 1 mod of X of I minus Y of I whole square. Actually mod for positive value. Getting our optimal the optimization is positively. Here also mod. Peak signal to noise ratio, PSNR. Peak, S for signal, N for noise or for ratio. 10 log base 10 A square divided by MSC, where A is a peak intensity value. A is the peak intensity value. Some compression standard names. For images, CCITT group 3, CCITT group 4, JBIG1, JBIG2, JBEC LS, JBEC 2000, PMP, GIF, PDF, PNG, KFF, etc. For video, DV, H.261, H.262, H.263, H.264, MBEC, MBEC 1, MBEC 2, MBEC 4, MBEC 4, AVC, AVS, HTV, JBEC, VC1, VME, V9, etc. Average length and entropy. Consider a source of n discrete symbols xn, n equal to 1 to n, 1 to n, each taking one of m discrete values. P of xj equal to an equal to pn, n equal to 1 to m. Okay. M discrete values. Sorry. If the number of bits used to represent an are equal to I of n, then average number of bits per symbol is L average equal to summation of n equal to 1 to m, 1 to m pn, that is p of x j equal to an equal to pn, then ian yeah, yeah, this one i of an, I of m, okay, an are equal to I of n, okay. Average length and entropy. Assuming symbols to be IID, the entropy is given by H equal to minus summation of n equal to 1 to m pn log to pn. Okay. That is, assuming symbols to be IID, the entropy is given by H equal to minus summation of n equal to 1 to m pn log to pn. Shannon's source coding theorem says that a code can be designed so that minus log base to pn less than or equal to I of an less than or equal to minus log to pn plus 1. Multiplying by pn and summing, we get that h less than or equal to L average less than equal to h plus 1. Huffman code. Shannon's theorem gives a bound but doesn't show how to achieve this. Uh, Huffman coding algorithm gives a code that satisfies this bound. It is instantaneous, uniquely decodable block code. This instantaneous, uniquely decodable block code. Example Huffman code. Symbol probability code. A2 probability 0.4 code 1. A6 probability 0.3 code 00. Symbol A1 0.01 code code is 011. Symbol A4 is having probability 0.1 code 0100. Symbol A3 having say probability 0.06, it is code 01010. A5 symbol having probability is 0.04 and its code is 01011. L average 22.2 bits per symbol, while log base to 6 equal to 2.585 and h equal to 2.14 bits. Example vector Huffman code. Symbol probability code A, B, C. For A symbol 2 by 3 probability code is 1. For symbol B having probability 1 by 6 code 01. Symbol 6 having probability 1 by 6 code 00. L average equal to 4 by 3 bits per symbol. Example vector Huffman code. Symbol probability code. For AA symbol probability 4 by 9 code is having 1. For symbol AB 1 by 9 011. For symbol AC 1 by 9 probability 0101 code. For symbol BA probability having 2.9 code 0100. Symbol PB 1 by 36 probability code 00111. Symbol here BC probability 1 by 36 code 00110. Symbol CA 1 by probability 1 by 9 code 000. Symbol CB probability 1 by 36 code 00101. Symbol CC